Hello, welcome to this video on Schrödinger's equation. Now, Schrödinger's equation is a really elegant equation and it has so many applications, well worth doing a fairly accessible video on deriving it, where we'll explore the wave function and what Schrödinger's equation has to do with the wave function. But before we get kind of going with some maths and some cool physics content, we're saying, because this video is fairly long, I'm using one of my favourite mugs. This is a mug I would really recommend getting. It's a really good mug because it has so many of the wonderful equations of physics in. We've got F equals ma. We've got the Euler equation, e to the I pi 1. And, if you want a physics-themed mug to watch physics videos with, this is definitely one worth looking into. And I'll see if I can, find a link to it and then paste it below this video. But anyway, now I've got my trusty mug with me ready. Let's get kind of cracking with Schrödinger's equation. So the first thing really to cover is why do we care so much about Schrödinger's equation? Are physicists just obsessed with looking into boxes and working out whether cats are dead or alive? But it turns out Schrödinger's equation talks a lot more than about cats, although to an extent it describes cats as well. Because Schrödinger's equation describes the fundamental properties of kind of materials and matter, providing that material is not relativistic, which for our purposes, often means the atoms or particles or molecules that make up that object don't have a huge amount of energy. So we're dealing with objects at kind of everyday levels of energy. Really non-relativistic energies. So the laptop you're watching this video on, or the mobile or tablet, has electronic components described by Schrödinger's equation. The mug of tea or coffee you're drinking from has Schrödinger's equation. If you're being a real rebel, the mug of chocolate you're drinking from is also described by Schrödinger's equation. As are gases, how much energy you have to supply to heat a gas at various temperatures is once more described by Schrödinger's equation. In terms of some kind of, I think, really cool applications, one application is semiconductors in electronic circuits. So semiconductors, it's easy to fine-tune how much electrical current they produce by changing conditions or their composition slightly. For example, the number of free electrons that can conduct electricity will depend upon the temperature of the semiconductor. And they have this ability to fairly easily change the number of conducting electrons by being able to essentially have a very small band gap between electrons that can conduct electricity and electrons which might like to but can't for various physical reasons. And this band gap is a consequence of Schrödinger's equation. When you apply Schrödinger's equation to ordered crystalline solids, you get band gaps, which is very analogous to how energy levels are spaced in an atom. So Schrödinger's equation describes semiconductors, and in fact allows semiconductors to exist, because without the band structure which Schrödinger's equation predicts, we wouldn't have semiconductors in the first place. Schrödinger's equation can also, as I've alluded to, describe atoms and energy levels in atoms, but it can do more than just describe the energy of electrons. It can describe their angular momentum, and when you take into account the angular momentum and quantum numbers like spin, you start describing the more richer, full structure of the atom, including subshells and orbitals, which, impacts things to the extent where molecules like benzene rings can form, which wouldn't be possible if it wasn't for the existence of subshells, which Schrödinger's equation can predict. And another application, there's so many of Schrödinger's equation, and the last one we'll talk about before we get on to talking about the wave function and what Schrödinger's equation has to do with it, is superconductors. Now, superconductors are hugely useful because essentially superconductor, what's acting like one, can levitate above a magnetic field. Well, I should say levitate above a magnet due to the magnetic field it is experiencing. And this effect could be incredibly useful in the future because, if you look at things like trains want to go as quickly as is safely possible. But a massive difficulty with getting trains past a particular speed is that there's a huge amount of friction between the moving train and the tracks the train moves on. If you can get rid of this friction, this train can move a lot faster. And one way you can do that is if you put superconductors at the bottom of a train, make the track magnetic, you then have a levitating train. However, the difficulty with doing this on an industrial scale is superconductors kind of lose their properties, thanks to thermal excitations destroying quantum correlations between conducting electrons. In the superconductors. The superconductors lose their property when their temperature goes, above a few Kelvin typically. So unless a semiconductor is really, really cold, it's not going to have any of its, amazing properties. However, who knows? If we get better at understanding quantum mechanics, we might one day be able to have semiconductors or things that work analogously to them that can operate at room temperature, and that might allow levitating boards, it might allow levitating trains and cause a whole kind of revolution in travel, kind of lead to a very futuristic world. So maybe superconductors and therefore Schrödinger's equation could revolutionize the world and make it, even more miraculous than technology has already made it. So the best place to begin is to look at the kind of object, the mathematical description of the state of a system that Schrödinger's equation is concerned with. And that thing is a wave function. Now, in classical physics, we don't need a wave function, but in quantum physics, we do. The reason is that in quantum physics, it is impossible to know both the position and the momentum of a particle simultaneously. Meaning that there is uncertainty, natural uncertainty, in often both where the particle is and what momentum it has. And this uncertainty relates to the uncertainty of what position and momentum will end up measuring the particle as having, but it turns out when the particle isn't observed, the uncertainty really describes how the particle feels like it is spread out in space across a certain, spatial distance, referring to the uncertainty in position, and similarly the uncertainty in momentum describes a particle which is genuinely acting like it's spread out in its momentum state, or we could say it's spread out in momentum space, because we often describe the states using vectors, and so we can consider a kind of abstract space built out of those vectors describing a particular state, and we call such a space a state space. Now, since position and momentum seem to be spread out, if you like, for the particle, or I should say the particle's position and momentum is spread out, we need really a function to describe this, to describe the kind of spread out nature of position and momentum, because that's what functions can do. Functions are kind of naturally spread out. Like if you look at, a quadratic function, a cubic function, that they're spread out in space. And this function, it turns out, will refer to the probability of us measuring the quantum particle in a particular position or in a particular momentum, depending on what the input to this function is. And we call this function a wave function. And a wave function has to be complex. It can't be, as it turns out, a real function due to Schrödinger's equation, which we'll see when we get to Schrödinger's equation at the end of this video. And usually, when describing this function, we use a trident-like symbol. It's the Greek letter psi. You'll sometimes see me put psi and then brackets, and inside the brackets x and t, to indicate that the wave function I'm concerned with in this video is a wave function of space, so the position x and time t, because you could in principle talk about wave functions that are functions of momentum if we're considering measuring what momentum a particle has, but the easiest place to begin is to consider wave functions that are describing the spread out nature of the position of a particle, or in other words, the probability of us finding a particle at a particular position in space. And Schrödinger's equation is concerned with how such a wave function will evolve. So it's concerned with the rate at which a wave function is changing. So this is very important because we want to know, for example, things like what wave functions describe particles which can be in a state and that state remains stable. So the particle isn't going to naturally go to other states. So Schrödinger's equation can tell us what are the stable kind of states of a particle or a system made up of lots of particles. Schrödinger's equation can also tell us about how the state will change if it does change, and therefore the dynamics of quantum systems. And so Schrödinger's equation is immensely useful. I mean, without Schrödinger's equation, we couldn't really do non-relativistic quantum mechanics, and therefore we'll probably never get to relativistic quantum mechanics or quantum field theory anyway. Schrödinger's equation is vital to quantum mechanics. Doing quantum mechanics without Schrödinger's equation would kind of be like trying to do classical mechanics without Newton's laws. And there are other ways of writing Schrödinger's equation. There are other approaches to the formulation of quantum mechanics. Just as, there are ways of discussing kind of the behaviour of a classical system which doesn't use Newton's laws directly, but uses things like Lagrangian mechanics or Hamiltonian mechanics. But, you know, just as Newton's laws is at the heart of classical systems, Schrödinger's equation is at the heart of quantum mechanical systems. You know, because physics is ultimately about trying to work out how a system changes in time. And Schrödinger's equation just discusses that for a quantum mechanical system, providing we're not worrying about relativity. So providing that system doesn't have, you know, relativistically high energy particles. So I mentioned that Schrödinger's equation is about the probability of a particle being in a particular state when we measure it, or equivalently how spread out the state of the particle is before measurement. So to understand the wave function, we need to understand probability and how probability relates to it in some mathematical detail. So it turns out that the square of the kind of amplitude, if you like, of the wave function, so essentially kind of almost the intensity of this wave, describes how concentrated the probability is in a particular point in state space. Now that might sound a bit abstract, so what I really mean is if we're considering a point, say, in position space, so a wave function is going to be a function of position, we might ask, what's the probability of us finding this particle in between the position x0 and x0 plus dx, where dx is an infinitesimal a displacement along the x-axis. Well, it turns out that the probability of finding a particle between those two infinitesimally separated points is equal to the amplitude of the wave function squared at that point in space, multiplied by the distance between our two infinitesimally separated points. So in other words, like the magnitude of the wave function squared is kind of like the probability of finding a particle between 2 points divided by the distance between those 2 points in the limit where that distance becomes infinitesimal. So the wave function, well, the magnitude of the wave function squared is kind of a measure of how concentrated the probability is. So essentially, if the magnitude is higher, you are more likely to find the particle at a particular point in space, and if the magnitude of the wave function squared is lower, you're less likely to find it there. That's the idea, really. Now, it's worth saying that this interpretation of the wave function actually only arose after Schrödinger's equation was formed. However, you know, in terms of understanding Schrödinger's equation, it's actually easier to start with this, and then we'll build to Schrödinger's equation. But worth mentioning for those of you interested in the historical development of quantum mechanics, we're not following the historical development here. So we'll just have to take it for granted, really, that the magnitude of the wave function squared is some kind of probability density. But we'll see that this helps us build towards Schrödinger's equation. Now, the thing we know about probability is probabilities have to add up to 1, which is essentially saying something has to happen, or we have to observe something. Now, for example, if you roll a dice, you might not know what side is going to be face up on the dice when the dice stops rolling, but you'll know one of the sides will be face up. You know, you're not going to roll a dice and then find that there's no faces, you know, face up on the dice. So we have to find some outcome, and therefore probabilities have to add up to 1. It's certain that we will observe some state, and we might just not know what that state will be. And because of quantum uncertainty in quantum mechanics, we definitely won't know what state that is going to be. But because the probability density, so how concentrated the probability is, or if you like, probability per unit volume, if that volume is infinitesimally small, is given by taking the magnitude of a wave function and squaring it. The total probability in a region of space is just going to equal the probability density integrated over all that space. Or, for quantum mechanics, the integral of the magnitude of the wave function squared integrated over that space. And therefore that must equal 1, because that's the total probability. Our equation here really just says that when we measure where the particle is, we have to find the particle in some location in space. So the total probability contained within a wave function, if you like, must equal 1. Now, in the last slide, I mentioned the idea that the integral of the size of the wave function squared over all state space for the particular state quantity the wave function is trying to describe has to equal 1, and that has to be true, because the kind of we're bound to measure the particle as having some value for that particular state when we observe that particle state. However, it's worth saying that there is a kind of assumption we're sneaking in there, which is worth talking about, particularly on this channel, where there's a playlist on quantum field theory, where that assumption wouldn't necessarily hold. And this assumption that we're making here is we are assuming that a particle that exists will continue to exist. Because if a particle that exists continues to exist, then yes, we are bound to measure that particle as having some value for a particular observable. However, if a particle exists but then ceases to exist when we try to measure the observable for that particle, we won't measure anything, because there's no particle there to observe anymore. At least that particle isn't there to observe. So we are really assuming that we're not worrying about particles being fundamentally created or destroyed. We can still describe particle interactions, and therefore we can still do kind of low energy particle physics and things like scattering and that kind of thing. We just can't deal with the particles being actually fundamentally created or destroyed. So because of that, because a particle has to always be present and the wave function of the particle has to always be present and preserve the total probability, we can say, as we said before, that the integral of the size of the wave function squared integrated over space has to equal 1, and this has to be true for all time. And since 1 is a constant, it's just a number, if we differentiate 1 with respect to time, we'll get 0. So, we can conclude that the differential with respect to time of the integral of the magnitude of the wave function squared over space has to equal 0. We can also write that slightly differently. We can just go the integral over space at one moment in time, t0, has to equal the integral over space at another moment in time, t1. And you know, that leaves us with the equation in this ellipse here. And this is important because it tells us something about how the spatial part of our wave function and how the part concerned with time evolution are going to relate to each other. They have to relate to each other such that when we put them together to get the wave function in space and time, the wave function obeys this kind of equation. And that places heavy restrictions, not so much on the spatial part of the wave function, but on the part of the wave function describing time evolution. And so how the total, or I should say overall wave function, is changing with time, which is very important because Schrödinger's equation is all about how the wave function changes with time. So now we've talked about the wave function, and we talked about uncertainty in quantum mechanics and how we get probabilities of finding a particle in a particular state from the wave function. It's worth talking about how this probabilistic concept of a wave function and the fuzzy nature of the quantum world will impact the kind of rules we can give for how a particle can evolve, or how generally a quantum system can change with time. And that will tell us something about kind of how to think about Schrödinger's equation. So in classical physics, you know, a particle has well determined position and momentum and behaves like it, you know, both when observed and when unobserved. And therefore, if we're considering how the particle changes with time, we can easily just envisage the particle moving. You know, with a particular set velocity at each moment in time. And this leads to the notion of a trajectory. So, you know, evolution equations for a classical system tends to talk about, at least if we're thinking about mechanics, the motion of a particle. It talks about trajectories. And so the concept of motion is a very natural way to talk about evolution, at least dynamical evolution, of a classical particle. And even if we're considering a classical object made up of many particles, really the evolution of that whole classical object is just dependent upon the evolution of its constituent particles, and therefore really all of, you know, the evolution in classical mechanics boils down to the idea of trajectory and motion. And particles will move generally to kind of minimise their total energy, and so they will try as best as they can really to find where the potential is at its minimum. Now they might oscillate about this minimum point, but they will try to get to this minimum point. And this leads to the idea of a potential well. So here we have a potential well describing the potential a kind of mass fields as it's kind of like oscillating back and forth when attached to a spring. Because if we imagine stretching the spring and then releasing this mass, assuming there is no energy loss from the system, this mass will keep oscillating back and forth, and it will keep oscillating back and forth about a point where the potential is minimum, i.e. about the position where the spring the mass is attached to is at its natural length, and so is it stressed or compressed from the length that we usually have. and we call this point 0. A, the capital A we can see on our horizontal axis refers to the amplitude of the oscillation, and we've got a potential energy V. In both quantum mechanics, in quantum mechanics we tend to use V for potential energy. In classical physics we use U for some reason, I don't know why, but we can clearly see that the potential energy, as we would expect, varies based on the position of the mass. So when the mass is at point 0, the spring is at its natural length, so the mass isn't experiencing any forces, and so the potential energy in the spring is 0. But as the mass moves kind of further away from that happy place, if you like, the spring gets more stretched or compressed depending on the direction and motion of the mass, and so there builds up more and more potential energy in the spring, and that's why we get this kind of like quadratic shape. Well, at least symmetrically rising shape, if you like. And the equation half k a squared is essentially the equation for the potential energy in the spring, so what we call the elastic potential energy, where k talks about the stiffness of the spring. So because particles in classical mechanics have well-determined position and momentum, they can naturally find this potential, this minimum of the potential, and do what they can to essentially move there, although they might oscillate about this point. And this leads to a very clear notion of both trajectory and how trajectory is related to forces or associated potential energy of those forces. However, the notion of motion is not valid in quantum mechanics for the very simple reason that although the potential might exist, a quantum particle does not behave as if it exists at a single point in space or at a single position, at a given moment in time. A quantum particle behaves as if it is spread out, and that means that the concept of moving is no longer a very sensible concept to use, which we'll come on to talk about in the next part of this video. Now we've talked about why time dependence may cause a particle to be able to move. In classical mechanics, we're going to talk about why the notion of motion is kind of redundant in quantum mechanics. And the reason it's redundant in quantum mechanics is that in quantum mechanics, a wave function is, typically spread out across the entire universe. In many ways, it's kind of a field. So, in a sense, the particle is everywhere. Now, given the particle is everywhere, it clearly can't move from somewhere where it is to somewhere where it isn't, because there are no places where it isn't, and it's already, in all places to begin with. So we can't really talk about motion in quantum mechanics at all. What we can talk about is the shape of the wave function changing, and that might give rise to the idea of probability density moving from one region to another, which under the right conditions might give the particle a behaviour where classical physics is a really good approximation, and the idea of motion can be kind of retrieved from that. Now, since we can't really talk about motion in quantum mechanics, the potential can't act to cause a particle to move, but since potentials will clearly affect the behaviour of our quantum particle or our quantum system, clearly they have to affect the probability density in some way, and so what a time-independent potential will do is it will tell you the shape that the wave function has to take. So it will tell you about the form of this wave function. You know, you can get that from using Schrödinger's time independence equation, which is an equation you can get from the time-dependent forward one, which we're kind of deriving in this video. But the shape of the wave function as deduced from the time-independent potential is not particularly intuitive, because as well as there being a desire in principle to minimise the overall potential energy of the particle and have a wave function which will do this, there are other principles which come into play. Principles such as necessary symmetries of the wave function, principles like if you change the shape of the wave function in physical space, you'll change it correspondingly in momentum space, which might mean, having a high probability density where the potential is minimum might mean that you have a high probability density of momentum, at large momenta, which might mean that actually minimising the potential might not be favourable. So there are a lot of things that come into play to work out the shape of the wave function and making it quite unintuitive, but a time-independent potential will cause a time-independent shape of a wave function, where this wave function can be extracted through this potential. So on the last slide I made a slight kind of simplification. I said, and it's something that will work for this video, but I did say that a time-independent potential will cause a time-independent wave function. Cause a time-independent shape of the wave function. Now that's not really strictly true, it's worth saying. I'm putting this here for those who are interested in exploring quantum mechanics further, or maybe have already seen exceptions to this rule. And an exception pops up if we're considering uncertainty in energy. So if we've got a particle where its energy is uncertain, so there's some inherent quantum uncertainty to do with the energy of the particle, then if we have a kind of well-determined classical potential, the only place for that uncertainty in energy to come from is uncertainty in momentum of the particle, or in other words, uncertainty in the kind of kinetic energy the particle has. But if the particle has uncertainty in momentum, that will affect the shape of the wave function in momentum space, because the uncertainty in momentum is kind of described by the shape of the wave function in momentum space. But due to Heisenberg's uncertainty principle that relates position and momentum, this impact on the shape of the wave function in momentum space will cause an impact on the shape of the wave function in physical space. And due to this, if you have uncertainty in energy, you don't have to strictly get a time-independent shape of a wave function in physical space, even if the potential is time-independent. And obviously, if you have a time-dependent potential, you're free to have a time-dependent wave function, such as when you're considering particle interactions and things like scattering. However, for our purposes, we're going to only be concerned with particles with well-determined energy, such as, electrons in a stable state in an atom, and we're going to assume that the potential is time-independent, again, like for electrons in a stable state in an atom. If we assume those two things, so time-independent potential and well-determined energy, then we have a time-independent shape of our wave function. When I say shape, I really mean if we draw a contour map with each contour line showing regions in space where the magnitude of our wave function has a fixed value, then this contour map won't start changing. So the amplitude or the magnitude of our wave function won't vary with time. And physically we can think, well, if we've got a particle where it's in a potential well and the potential well isn't changing in time, then that particle is going to want to have, a wave function where that wave function, if we consider that wave function across all of space, is kind of shaped in such a way where, if you like, the average, if that's the right word, total energy of the particle is minimized as much as possible. And so essentially there's no incentive for the wave function to change if the potential isn't changing, because if the wave function is minimizing in some abstract way the overall energy of the particle and the potential isn't doing anything, then if the wave function was to change its shape, the particle would have correspondingly higher energy, and that's not what the particle wants to do. Also, if you've got time-independent potential, as we can see from experiments and stuff, we don't really get, unless we're worrying about uncertainty and energy, anything like the classical notion of motion. And motion is to do with the probability densities of a particle being at a point in space varying from one time to another, such that as time passes, probability density moves from one region in space to another. So if we think about it like that, we can say, well, the time derivative of the probability density should be 0, so the probability density shouldn't change with time if we have a time-independent potential, so we don't have anything like classical motion. And using the rule of complex numbers, which extends to complex numbers such as our wave function psi, you can show, if you want, quite rigorously, that the top equation does imply, as we expect, that the rate of change of the modulus size of our wave function is 0. So the magnitude or size of our wave function is a constant with respect to time. And this is very important because no matter how the wave function evolves, this condition must be true. And that tells us a lot about what form the time dependency of a wave function can take. Because however psi of epsilon t evolves, the magnitude of psi of epsilon t has to be a constant with respect to time anyway. So we now got two very important conditions for our wave function, at least the wave function of the particles we're interested in for this video. So one condition is that the shape of the wave function of our particle is time independent. The other condition is that our wave function can in principle contain time, so the time has to be somewhere in our overall wave function. And we're now going to bring these two things together to understand the form that the time dependence of the wave function actually takes for such a particle. So to do this, we really use Occam's razor. We think of the simplest way of achieving both of these assumptions. So if we consider the assumption that the shape of the wave function isn't changing, by which we mean the probability density associated with finding a particle in a particular region of space is time independent. Well, in this instance, because the probability depends on the magnitude of the wave function squared, we can just go, well, the probability of finding a particle in a particular region of space is a thing that should just depend on spatial coordinates. We shouldn't be worried about time, because if I ask what's the probability of finding a particle in this region, whether I'm asking that question at 2 p.m. or 5 p.m. shouldn't matter. Because if we're assuming the probability is time independent. And so associated with the time independent probability should be a time independent wave function. Or at least part of the overall wave function should be time independent. And that time independent part is to do with probabilities in space, physical space, and therefore that part of the overall wave function should be the spatial part of our overall wave function. So the simplest way to have a time-independent probability density for position of a particle is to have the wave function describing the position of a particle to be time-independent. But our overall wave function still has some time dependency there, and putting those two things together, we can see that clearly the spatial part is independent from the time part of our overall wave function. But the same holds in reverse. The time part is independent of the spatial part of our overall wave function. So we can clearly split our overall wave function into a spatial part, which I'll call psi of x, and the time-dependent part, which I'll call psi of t. And the question now is, how do we go from the overall wave function to an understanding of psi of x or psi of t? Well, for that we need to know how psi of x and psi of t together construct the overall wave function. But it's worth remembering what the wave function is. The wave function is something where when we take the size of it and square it, we get a probability density. So the magnitude of psi of x squared is going to be the probability density for finding a particle at a point x in space, and the magnitude of psi of t squared is going to be the probability of finding a particle existing at a particular moment in time, t. And these probabilities should be independent from each other, because there's no inherent connection between position and time. And so we would expect, therefore, that we get the overall probability of finding a particle at a particular point at a particular time. In other words, we get the magnitude of psi of x and t all squared by multiplying the probability of finding our particle at position x by the probability of finding our particle at time t. And this argument for probability applies also to probability densities. And so, writing that using the mathematical notation we have developed, we can just say in a more mathematical way, the magnitude of psi of x and t all squared is equal to the magnitude of psi of x squared times the magnitude of psi of t squared. And now what we can do is we can fuse the psi of x and psi of t together. Because using kind of rules of kind of algebra for complex numbers, which applies equally to complex functions, we can rewrite the top equation as our equation here, and this will clearly work if psi of x and t is equal to psi of x times psi of t. So the overall wave function is equal to a spatial part of our wave function times a time-dependent part of our wave function. So we now said that we want the magnitude of the overall wave function to be time independent, but we do want a time-dependent part of our overall wave function. And we can put these things together to understand an important property that psi of t, so our time-dependent part of our wave function, has to have. Now remember that all the evolution of our overall wave function is contained in psi of t. And also our overall wave function is given by multiplying psi of x and psi of t together. And as we say, the magnitude of the overall wave function is time independent, so the derivative of the magnitude would be 0. Well, we can now substitute for the overall wave function the time and space components of the wave function, and we have this. Now, our time derivative is going to act on something that varies with time, so it's going to act on psi of t, but psi of x won't really notice this time derivative at all, because psi of x is a time independent part of our wave function, so it's kind of not going to depend on time in any way. And so we can pull that out. And now if we think about possible solutions, well, just dividing both sides by the magnitude of psi of x, we get that the time derivative of the magnitude of psi of t is 0. Now, you might go a very simple solution for psi of t that will satisfy this equation, this idea that the magnitude of psi of t cannot change with time, would be if just psi of t was 0. Because clearly the time derivative of 0 would be 0. However, that doesn't work, because if we go psi of t is 0, then psi of x and t, so our overall wave function, would have to be 0, meaning our particle would be impossible to find any state, well, in any state whatsoever. It simply wouldn't exist. Also, we know psi of t relates to the probability density of finding a particle at a particular moment in time, and so if psi of t is 0, then we're saying a particle doesn't exist at any moment in time, which would obviously mean a particle doesn't exist. And given we want to talk about the quantum mechanics of existing particles, not particles that have never existed, clearly we don't want to put psi of t equal to 0, but we want the size of psi of t to be time independent. We also would like psi of t to evolve in time, otherwise it's very unclear how we can, if we loosen our restrictions of time independent potentials and well-determined energies, get a quantum mechanical system to start under the right conditions behaving classically, such as starting to move, or doing very unclassical things like neutrino oscillation, which would imply that, clearly psi of t would have to have some time dependence in a wide variety of situations. So although for the purposes we're dealing with the magnitude of psi of t is 0, we wouldn't really want psi of t itself, for our purposes the magnitude of psi of t is time independent. We don't want psi of t itself to be time independent. In other words, we still have to allow for the possibility that the time derivative of psi of t doesn't equal 0, even when the time derivative of the magnitude of psi of t equals 0, which is an important thing to remember. And so now we're going to get to what form psi of t could take given these two restrictions about time derivatives concerning it. And this will tell us all we need to know to write down Schrödinger's equation, because all the evolution of our overall wave function is contained within psi of t. So we now got everything we really need to get the time-dependent part of our wave function. So, we said that we want the magnitude of our time-dependent part to not change with time, so we want it to equal a number, but we want really to contain the possibility of dynamics if we relax conditions like we allow, for example, for uncertainty in energy. We want the time-dependent part to still change its output if we give it a different time, even though the size of it has to be preserved. So we define psi of t to be a complex number of a fixed magnitude. Now, because of normalization we have to do, it just makes sense to set the size of psi of t to 1. If you set it to any other number, you're going to have to cancel out that number by a normalization factor when you try to normalize the overall wave function. So, for simplicity, we just set the size of psi of t equal to 1. And so psi of t is a unit complex number with t as an input. So, a complex number, a unit complex number, is you have the form e to the I theta, if it's a function of theta. But because of essentially not wanting lots of minus signs to appear later, such as when we get to Schrödinger's equation, it actually turns out we're writing the unit complex number in the form, e to the minus I theta. But we're free to do that because that's also a complex number. I mean, a lot of the times it doesn't really matter. You can do it either way. We could say psi of t was equal to e to the iat, where a is some parameter, or e to the minus iat. But to avoid minus signs later on, we put a minus sign here for now. Now a is a parameter, and you might guess, given that a complex number, a unit complex number is just kind of like a point, if you like, orbiting around the complex plane, that a is going to reflect how quickly the output of our psi of t changes with time, so how rapidly this number moves about the complex plane. And t, bearing in mind, is are just parameter. Well, t is time and a is our parameter. And also, it turns out the simplest thing to do, which also happens to work, is just to set a to be a constant. You could also have a to depend upon time, and you'd still have a unit complex number, but it just makes matters a lot simpler if a doesn't depend on time, and a lot of the time that seems to actually work. So now what we need to do is work out what this a could be, write it in terms of constants, like we don't have any Planck constant or reduced Planck constant appearing yet, which indicates we still have a tiny bit to do, and that will bring us to Schrödinger's equation. So remember, psi of t takes this form, and we can differentiate both sides with respect to time, and we get this. And if we want to work out now how our overall wave function changes, we remember that our overall wave function is equal to psi of x times psi of t. Psi of x is importantly time independent, so all these change occurs in psi of t, and psi of t evolves according to our middle equation. And so, bearing in mind that psi of x is affected by a time derivative, we can just say the partial derivative of our overall wave function with respect to time is equal to minus I times a times our overall wave function. Now, bearing in mind that, 1 over I is the same as minus I, sorry, is that the right way? Yeah, it's a slightly strange thing with complex numbers. functions, but 1 over I is the same thing as minus I. We can rewrite our partial derivative equation in the bold equation here in blue, and now we can compare units. So the units of psi, our wave function, is somewhat debatable. So you could go, well, the magnitude of psi squared is probability density, which is probability per unit volume, in the limit that volume becomes infinitesimal. So you might go, well, probability density has units of, say, per meter cubed, because probability is dimensionless and volume has, in standard units of meter cubed. Meaning you might go, well, probability density when square rooted should have units of like meters to the minus 3 over 2, so the square root of per meter cubed. And you could do that, and because psi appears on both sides of our equation, you'll get the exact same answer for the units of A if you just went, well, psi is kind of like related to probability density, but although probability density is probability per unit volume, although that volume is infinitesimal, and so it doesn't really have any physical meaningful size, and so really probability density should be unitless, it shouldn't have any units, meaning our wave function, which is the square root of our probability density, also wouldn't have any units. But either way, to balance the units on either side of our equation in blue, we require that A times T doesn't have any units. And that tells us something about what A could possibly be. And it's what A could possibly be that brings in Planck's reduced constant, and therefore leads us to the final form of Schrödinger's equation. So, remember, we have this equation. We used it to justify that essentially A must have units per second. Now that's relating to some kind of frequency. A is telling us about the frequency at which the time-dependent part of the wave function is oscillating, as the output of the time-dependent part of our wave function moves through the complex plane. Or I should say moves through a circle on the complex plane. Now, with frequency, one could be talking about linear frequency, but in physics we tend to use angular frequency. And that's useful if we're talking about, linking oscillations to circular motion, because circular motion is periodic like oscillation, so it's a sensible thing to do, and there are other reasons to talk about angular frequency. One being that there's a very special equation with angular frequency in, and it's an equation that relates the energy of a particle to the angular frequency of that particle. The equation says that these two things are proportional, and that makes sense if you think about electromagnetic waves composed of photons, because you'll probably know that if you have a photon with a very high frequency, so in other words omega is really large, then that photon is going to have a lot of energy, which means it might be quite dangerous. That makes kind of high frequency electromagnetic radiation kind of ionizing, which is why X-rays are ionizing, gamma rays are ionizing. But when you go down to very small frequency waves, like radio waves, they're not ionizing because the photons don't have much energy. Because if we make the angular frequency small, our equation tells us the energy of the photon will also be small. So this a fact we see on a daily basis, and that's why you have to be careful of some types of electromagnetic radiation more than others. What relating energy and angular frequency is constant h bar, and this appears a lot in quantum mechanics. But given that A has units of angular frequency, we can just, well, the simplest thing is to just go, well, A is the angular frequency. And that makes kind of sense because a particle is described in quantum mechanics by a wave function, and the angular is telling us how rapidly this wave function is oscillating, so it's telling us about the angular frequency of the wave function. So it makes sense to go, well, omega and A are very possibly the exact same thing. Well, if we go omega as A, then our kind of equation really originally for photons, but now we're applying it to other particles as well, reads E equals h bar times A, which we can rearrange to A equals E divided by h bar. And if we plug that into the differential equation we have at the top left, we get Schrödinger's equation. And this equation here, this kind of equation in our box, is Schrödinger's equation. Now, because physicists are lazy, to be honest, we don't like writing a lot. Possibly because there's so much to write about in the universe. If we liked writing, we would get precious little studied in terms of how much there is to learn about the world. So we invent something called the Hamiltonian, which is just I times h bar times the partial derivative with respect to time. It's essentially a differential operator. It's a very special one. It relates to the energy of our particle through the eigenvalue equation. Although as h bar relates to the energy of our particle, that's not too much of a surprise perhaps. But using the Hamiltonian operator, we can rewrite Schrödinger's equation as just the Hamiltonian operator acting on our overall wave function is equal to the energy of our particle times the overall wave function. Thus, clearly they're showing the connection between the Hamiltonian operator and the energy of our particle. And this is an eigenvalue equation. Something you'll see if you do matrix algebra. If you would like to learn more about eigenvalue equations, please check out my linear algebra playlist. I think it's only got 2 videos on that at the moment, but it does talk about eigenvalue equations. So this is everything really for this video. There hasn't been much in terms of using it because there's so many bits to kind of unraveling the mysteries of quantum mechanics, where we're going from what assumptions can and can't we make in quantum mechanics to a very specific mathematical description of how the wave function evolves. So that was plenty for a single video. However, if you would like a playlist on solid-state physics and some applications of Schrödinger's equation, one might be coming up on this channel. I'm quite sure one will be at some point, but when I'm not too sure. But if you would like one, really soon, by all means, put in the comments. Or if there's any other bit of physics you would like me to cover, similarly, put it down in the comments, and I'll do what I can to make more kind of content, which will hopefully be exciting. And soon though, I do want to make a video talking about time and quantum mechanics. Okay, now we've got a time-dependent wave function, or at least we've got a part of our overall wave function that has time dependence. We can talk about some of the difficulties of uniting quantum mechanics with general relativity. And the problems emerge immediately you know, in Schrödinger's equation. They're a bit more subtle if we look at quantum mechanical equations more well designed to deal with relativity, but some of the problems immediately emerge in Schrödinger's equation, and so I might make a video about that at some point. Time is a strange thing in quantum mechanics, and also, you know, fascinated by time, got a playlist on relativity going, so it seems sensible to talk about time from a quantum mechanical perspective as well. So yeah, that's everything for this video. If you do like the content, consider subscribing, checking out the other videos. But hope to see you for more soon. Also worth saying, I think at the moment this channel is, got it's got it's growing, but I think there's about 387 subscribers, but there's a poll asking about preferences for topics to cover for later playlists. So, you know, if you would like general relativity, string theory, or stellar evolution to be covered on this channel, you know, consider having a look at that poll. You know, I mean, it's over a month before I, you know, finalise what I'm going to do. But, you know, if one of those three topics is something you really like covered, have a check of that poll before we reach the end of October. But anyway, thanks for watching this video, and I hope to see you for more wonderful physics soon.